Okay. Maybe higher. Hello. It's on. Okay, maybe this is a good time to begin. This is not working, but it's okay. But I'll let you. I think it's on. It is on. Okay. Maybe put up the volume. Okay. I think this is a good time to begin. Good evening, everybody. My name is Leo Radzikowski. I'm a professor here in the physics department, and I want to welcome you all here this evening for this lecture. And before we turn it over to the lecture and introduce tonight's distinguished speaker, I wanted to say a few words to give you some background to this event. So this public lecture is an outreach effort by the Boulder Summer School for Condensed Matter Materials Physics that we hold here on campus at the University of Colorado every year for 4 weeks in the summer. So the school consists of, we invite, in a highly competitive process, we evaluate and invite 65 students from all over the world, PhD students and postdoctoral students, and to come to University of Colorado to live here for 4 weeks and to attend lectures, advanced lectures beyond sort of regular classroom level lectures. And these lectures are delivered by also, world-renowned scientists that are experts in the field of the school. Every year, the school is in a different subject. They have ranged from, subject of superconductivity, quantum computing, soft matter, magnetism, you name it. This is a 24th annual school. So we started in 2000. We skipped 1 year during COVID, unfortunately. Yeah, so we're back online, and this is, and many of our lecturers and organizers are actually past participants, student participants of the school. So it's really a pleasure to see them returning and really contributing to the condensed matter community through organizing and lecturing. Let's see. So the subject of this year's school is on self-organizing matter, which is kind of a hybrid subject, fascinating subject between condensed matter physics, soft matter condensed matter physics, material science, biology, and many others, like in chemistry, for example. So with that, let me turn it over to, and I should also say the school is supported by National Science Foundation, University of Colorado, and this year by University of Chicago, contributing to bringing students here and lecturers here. So with that, let me turn it over to Professor Margaret Gardell, who's going to introduce tonight's speaker. Please, Margaret. Yes, please.
Great. So it's my pleasure to introduce tonight's public lecturer, Manu Prakash. Manu is a bioengineer at Stanford University, and with a really far-ranging interests from physical biology to understanding how living system and life computes information from its environment to change its tasks. And more recently, his lab has shown a growing interest in understanding oceanic life and developing new tools and approaches to understand non-model organisms. Manu is an associate professor in the bioengineering department at Stanford and also has appointments in oceans and biology. I didn't know there were departments of oceans. He's also a senior fellow at the Stanford Woods Institute for the Environment. Now, the type of work Manu does is really creative. He's actually been at the forefront of driving and being in engineering, developing new engineering approaches and science approaches, and that's sort of told by his education. He started his education out in India at Indian Institute of Technology in computer science and engineering, and then got his PhD in applied physics at MIT. Right. So from there, he's really gone into this world of physical biology. For the creativity and really sort of remarkable results found in his work, he's won numerous prizes, including the MacArthur Genius Award, the Index Design Award, the Microbiology Society Unilever Colworth Prize, and the Ernst Abbey Award. I think one of the reasons that we were really excited as organizers to choose Manu is really he has this contagious enthusiasm and passion for scientific discovery. He communicates that within our scientific communities, but he's really spent a huge amount of effort and to make these tools available to the broader public in the topics that you'll hear about today. So with that, I'd just like to introduce Manu, and thank you very much.
So thank you all for coming. This is an absolute pleasure. I have around 600 slides in this slide deck. And, let's see. But, I think I want to begin by just saying something that, first of all, I'm sad that I haven't been able to spend as much time at the summer school this year. I just got off a boat, quite literally, and yesterday we talked quite a lot about just what does it mean to spend some time in ecologies and environments. I think I'm going to switch gears today and tell a slightly different pulse of the story, and you'll start realizing the links. And I think I grew up in India and thought quite a lot about what should we do with our time. And I think this is something that you all care about, you all think about. With your creative sets of abilities, we have to answer this question in our life. And I want to just tell you a little bit of a piece of a journey of how I spend my time. And then before I begin, interrupt me anytime. I happen to have some toys and tools with me. And the best questions can get some microscopes. So it's just, if you needed an incentive to interrupt, please interrupt at any time, because it doesn't really matter that I have to cover much of this. I really want to share the philosophical framework here. Okay, so I think with that, I don't work alone. It really is a remarkable group of students and postdocs in my lab. And now they've gone around the world to start their own lab following some of this frugal science philosophy that I'll talk about. So it really is a joy to have adventurous people carry on some of the things that we do. And I think some of the important aspect of this is also people bring their own self to the sets of problems. And I will describe to you certain problems where physics and physical thinking and the kind of quantitative thinking that you all embody is essential for problems that for the last even 100, 150 years have just remained and stared at our face. And it really is ironic and somewhat sad that some of the problems that I'll talk about are even problems till today. So if there is nothing you take away, I know it's evening, you can take a nap, you can doodle. I just want you to remember this one thing. I teach this class called Frugal Science. It's free for anybody to take. And last year, I had a student from Sudan, Marwan, and I was talking, we had a fantastic time. We were just about to initiate and start a very large-scale deployment of foldscopes, which I'll talk about in Sudan. He was interested in education, and this conversation was 2 nights before the war broke out in the capital. And we were having this conversation. He said, Manu, what much of the course has reminded me is this Sudanese saying, which is, don't make a pen that doesn't eradicate ignorance and shame. And pen, what he meant by that, this is a very old saying, is kind of a symbol of technology that's ubiquitously available. And I think often enough when I think about it, there are solutions littered everywhere, but if they don't actually solve the problems that we care about as society, sometimes because they're not accessible, sometimes because they are not made available very broadly, and sometimes because they are not applied appropriately. So I think this embodies for me a lot of what I'll talk about, but in a single sentence. Okay, so the first half of this talk will be very depressing. And I want you to be depressed because I am thinking about these things all the time and losing sleep. This is a picture that I took in Ghana. Currently, around 1 billion people in the world call this a hospital. This happens to be a shed, a car comes by, and there may or may not be a doctor. Most likely, there's a community health worker. And we talk about, access to health, but you have to remember, many of these kids might actually have malaria, which we'll talk quite a lot about. And one of our field sites in Madagascar, to be a little more quantitative about it, access to health is often driven by a last mile problem. Often, many of our solutions are centralized, and you can imagine and think about that distributing them from a global context is very difficult. And so very few countries around the world can actually achieve this. And this is literally our hike when we have NGO in Madagascar called Pivot that I'm on the board of. We literally have to travel 12 to 14 hours to reach any of the clinic. And the same applies for someone who's actually trying to come back. So I want you to have that in the back of your mind. You don't have to imagine a faraway place. Think about a mountain in Colorado. Think about essentially many of the sets of areas where primary health center is the only center that's accessible to people. In that context also is a large number of treatable diseases that we think we've had a solution for the last 50 years. I'll talk quite a lot about malaria. I just want to share with you this plot. We had a tremendous decline in malaria cases, primarily because of lots of new tools and technologies that were brought to the table. But for the last 5 to 10 years, malaria is back on the rise again. And what I mean by that is in terms of numbers of, hundreds of millions of cases, 300 or so, 300,000 million cases, for example, they're actually starting to rise. And, if you don't care about the graphs, this is another photograph that I took that actually haunts me quite a lot. This is in Uganda at one of our field sites in Tororo. And often enough, parents would bury their children right in their backyard, right in front, because they don't want to forget. So these kids are literally sitting on the graves of their brothers and sisters. And you see this across entire countries and places where you would move and travel. But this is literally for a disease that we've had a cure for a very long while. And if this was not scary enough, you actually realize that now, with climate as one of the criterias, there is what is called a rise of a super mosquito. This is Anopheles stephensi. This happens to be an urban malaria mosquito. Malaria has always been in pockets of rural areas. And for the very first time, it invaded through the Horn of Africa. And at this point, it's actually majority of Africa is covered. And people in the malaria community are deeply concerned that for the first time, a city like Lagos, with millions and millions of people, will actually have outbreaks of malaria. And we don't know how to handle something like that. And again, just yet another example from a vector point of view. Many of you know about what happened with Zika, yellow fever. This is not some faraway place. This is effectively the sets of when new vectors come and establish really tremendous challenges come along with it. I said a few words about health. I started working in health and global health 15 years ago, and I started realizing what a deep connection it has to education. You could build the best sets of hospital. If nobody shows up, what's the point? When we think about our context of education or science education, this is literally what a school looks like for a majority of the kids in the world. 2 billion kids, roughly around 1 billion kids live below $2.5 per day in a family. And even if they go to school, it's not what you might think you can acquire in a school. COVID was a great example of thinking about this. Literally 1/3 of the school children had no access to education. And I studied a lot of this in the context of India. And of course, the many sets of entities would like us to believe that we had all this education through mediums. That was literally what was happening. So, I don't know how you actually learn that way. And then I think, if you start moving even a scale larger, many of these sets of problems are visceral in our backyards. When you ask yourself of what's really happening on the planet, this is, I kind of call it the apocalypse paper. I would encourage every one of you to read it. This is 2017, where they showed that 3/4 of all insects across Europe, while you think it's not that much deforestation, have completely disappeared. There is no explanation till today of what this massive decline is caused from. And again, these are shifts in ecosystems, and this happened in last 25 years, right under our nose. 3/4 is a very large number to think about such an important ecosystem to actually disappear. We think quite a lot about the ocean in this context, so I'll give you an example of the sets of a challenge on what the planet and what's happening on the planet from an oceanic perspective. The ocean is not just a giant bath of water, it's an incredible ecosystem beaming with life. And our life depends on what happens in the ocean. So half the oxygen that you breathe, it is a massive reservoir for heat, roughly between 30 to 40% of all anthropogenic carbon that we emit in the atmosphere is essentially absorbed. And if this mechanism that the ocean uses to absorb this carbon was to be turned off, we would have 400 to 600 parts per million as almost an instantaneous change in the carbon in the atmosphere. So I want to take you to the ocean too, just a little bit, because I told you I was on a boat recently. This is what it often looks like when we work at sea. This is a massive reservoir of carbon, 40 times larger than any place that you can essentially imagine in terms of the terrestrial, the amount of carbon in the atmosphere. Look at that curve. You start realizing that, of course, we've been pumping carbon, and the ocean has been essentially taking on this curve. The right middle of that light blue curve on the top is essentially the sequestration process. So we are here because of this sequestration process, but what we don't understand as yet is how that sequestration even works and where there might be a tipping point. And, you know, the challenge for us as the physics community is, of course, tremendous work has been done to build the kind of models that have been predicted so far. But many of them do not have biological parameters. And most of the nonlinearities arise from many of these biological parameters because this is a living soup. And so one of the big challenges to be thinking about is how would we actually tackle that? And when would a tipping point for something like this? And I'll bring that in a second in terms of what the challenge is. And then, of course, it's a physics colloquium. I should talk about dark matter. My favorite dark matter is plastic. I know the other dark matter is also important, but these are two sides of the same coin. This one worries me. 99% of the plastic that we emit, we can't actually find. And of course, 88% of the ocean has been covered with microplastics. But one of the challenge of this is most of the time where it goes, and we actually have a little bit of a hint for where it's going, it's actually circulating in the ecosystem, which is these diel migrations that occur down below a kilometer. And when we do find it, this is how we find it. And I think from a context of rethinking materials, I mean, this is a community that designed and built remarkable materials. We have it upon us to be thinking about rethinking many of these sets of materials because this plastic eventually has now embedded all the way to, in some of the expeditions, we do these 4-kilometer trawls and you would find literally plastic in every single sample that we take. Okay, so that was the depressing part of the lecture. I want to share this with you because I lose a lot of sleep and sometimes I am obsessed about these sets of questions. And I think as a community, we cannot turn our eyes away from the problems that we see around us because many of the sets of solutions and things lies in people's minds and sets of ideas. And as humanity, we've done a tremendous amount of job. But at that same time, the next sets of challenges seem very daunting. Not just because it's not about, I mean, you know, when you look at COVID and you think about the Sputnik moment, technology did come across, but we also saw the cracks and the limits of what an approach of how we bring these sets of tools to people do. And, you know, of course, in the health kind of a context, Martin Luther King said this very well in terms of thinking about inequality in healthcare and justice, is the fact that unless these sets of tools and technologies that many of you will invent, unless they're accessible, I'm not sure they will have the kind of impact that you would like to have. So for much of the time, I will talk about access and thinking deeply about access from day one if you're interested in engaging in these sets of solutions. So here's the grand challenge. I like, you can choose which Earth you live on. By the way, that is 70% of the planet is covered with water. We often forget about that. But one of the challenges that we face in every one of these problems, that they are measurement problems when it comes down to diagnostics, when it comes down to environmental impact, when it comes down to be able to teach people to engage in this ecological changes that are happening. And then the second challenge, and at least the approach we have taken, we don't have enough scientists. You don't have enough doctors in this world till today. And you have to be thinking about a very inclusive approach where scientific tools and technologies can enable people to be able to do remarkable, important work in their communities. That must exist as our criteria that we are able to build these sets of partnerships. So, it's not as if we've not faced challenges. And I want to share an example from astronomy because I was very deeply inspired by when I read about. So just before I jump to astronomy, much of what I'll talk about is this philosophy that I've been calling frugal science. The idea is that cost and performance in scientific tools, ideas could actually be put as a design principle. So yes, you could perform something with $1,000, but could you do it for $1? And yes, that performance might come down, but then maybe 1 billion more people could actually have access to that tool. So when you're choosing your target of where do you want to solve, you should really be thinking about this design space early on. And one example of this is this object. I don't have to tell you what that is. Does everybody know what that is? Yes, it's the size of a basketball. This is Sputnik, the first satellite that was ever launched. It caused a panic around the world. I mean, it was a remarkable technological achievement, but at that time, at least in the US or anywhere, there was no tool that could track a satellite. So you could claim that I just launched a satellite. And they actually put a beeper in there, a radio transmitter to prove that. And Fred Whipple at that time, before the launch, he was the head of the Smithsonian. He was thinking about this problem. And he launched what I believe is the oldest citizen science program in the world. It was called Operation Moonwatch, which was literally $10, $20 telescopes distributed to tens of thousands of people around the world. And while he was building this network of a community, the military was essentially building what eventually became the Baker-Noon satellite trackers. Billions of dollars spent, but they were not ready. And eventually, for the next 30 years, it's these group of individuals that not only tracked every single set of a satellite, but much of what we know about satellites at that time and what we learned about came from these data sets. You might wonder why they're sitting on this particular grid. Is because they're collecting scientific data. You're given a grid, you actually calculate the trajectory, you send those sets of trajectories, you get the next day's parameters, and many of these Sputniks were actually tracked by these individuals. I pulled out a letter because I was hoping there would be some young people in this audience. And if you think about this, this is something that a 17-year-old at that time wrote. He said, I was 17 at that time, and I began freshman classes at the Northeastern. Then he talks a little bit about they were trying to organize themselves, sit in the night, and then he says, a few days later, we heard the team from Illinois was the first to spot the Sputnik in the booster stage. Finally, after 8 days of bad weather in the skies, I heard a person in their team shouting and describing the trajectory. And then he says that, oh, a couple days later, I was able to actually see because Sputnik 2 was launched right there. And then I love the last line. He says, sadly, my Moonwatch scope was stolen in 1963. And, this just kind of gives you that sense of moment of discovery by this person who is contributing to what was actually a national crisis at that time. So there are letters after letters. The person who designed the Hubble actually talked about it, of why he got interested in astronomy was from that moment to begin with. So, there are lights of hope. And I actually would argue that our community healthcare system is even a longer citizen science program per se, because these sets of individuals, this is from the Ebola crisis, this is last mile health. Now, this individual is heading out to a clinic in Liberia where she knows she's about to meet an Ebola patient. She has a high school degree. She's much younger than me. And she's going out there because that's our frontline workers. That happens around the world every single day. These are the individuals that actually protect us from some of the completely undescribed pathogens that are circulating on our planet. As deforestation is happening, we're actually driving new pathogens to come in, and these would be the frontline sources. WHO and many organizations have estimated that because many of these volunteers are unpaid, trillions of dollars are being subsidized primarily from these people. And one of the things that I think about personally is what can I provide to a person like that they could do their job better? And I think this is something that you have to think about. It's not technology by its own sake. It's technology in the hands of right people with the right sets of intentions. So this is really what you should think about in terms of solutions. We've spent a lot of time in the field talking to individuals, and many of the ideas that I would say is, if I could write every one of the names, these are thousands of people that have contributed. And it made us start to question what types of things we should do in the lab versus what type of things we should do out in the field. I remember as a young assistant professor, I went out with an idea and met that gentleman, Paul. Paul had been teaching pathology for almost 14 years by that time. And he said, Manu, you should come back to me when you can do diagnostics under a tree. I've really taken that to heart, and I'll actually tell you that now we can do diagnostics under a tree. It's taken 10 years, but I'm actually very proud of that moment where you have to face reality if you're out there trying to solve problems. We've done the same thing, 17 expeditions in the last 5 years on the context of the ocean. I'm just trying to reflect that when you engage in societal and ecological problems, it actually is important that you spend time in these sets of communities. And ideas come out that you would never realize sitting in your office, which this is one of our Arctic expeditions. And I don't know whether I'll talk about it, but it is also quite beautiful out there. So if you need an excuse to get out of your office, that's your excuse. Okay, so I think let me give you a brief tour de France into ideas and projects and how we've been trying to scale them. I don't intend to cover the 600 slides. Much of this is written. We share this. So if you believe in this philosophical framework, this is really just an invitation. And we really need lots of people with analytical ways of thinking about these sets of problems. And I'll make that very clear that these problems might sound abstract, but they can clearly be generalized. And many of the tools that you all carry are exactly what we need. Okay, so let's start with crisis. I don't know how many of you know the story of how bikes were invented. So, by the way, let me just ask a question about scaling. How many bikes do you think there are in this world today? Just a guess. You can throw out a number. 2 billion? 3 billion? Yeah? 4.6 billion, right? Anybody else? 1 billion? Yeah, I think you're so around 700,000. Less than a billion, essentially. So maybe around, I would say, 800 million. And one of the things around this is ideas that we take for granted also take time to scale. So, you know, it's something to keep in the back of your mind, that something that is just so important also hasn't, I mean, when I read that statistics, I was like, okay, you know, everybody should have a bike. But the context of this is bikes were invented when there was a massive volcano that killed horses because there was a famine in Europe. Because of the smoke, all the crops started to die. And of course, the famine went away, but the bicycles remained. And, you know, this is kind of an ironic thing in going back and thinking about COVID and crisis. So when you think about this crisis moment that we feel in the climate, you can look back and see that, yes, humanity as a whole in many crisis moments have done wonderful things. And, you know, but this is something that we have to take on as a challenge. So, you know, during the COVID time, many of my students, collaborator, Margaret was involved. Many of the students here I know were involved in these sets of processes. I mean, it was just a chaotic time, but at that same time, it was important to be thinking about these sets of challenges with a kind of a focus that I sometimes, even if I want to, I can't put together in. And so it is a testament to, I mean, this is just much of the work that we did in collaboration with people around the world, with literally in a year, products that I thought would take us years to build and design. We were building them in literally weeks and shipping them and interacting with people and the kind of collaborations that sparked. So I think we do need a moment like that in the context of the climate, and I'll come back to it. So I'm not going to talk about many of the projects, but now I'm just going to give you a flavor of ideas and show a little bit of that, the spark of physics that's actually hidden in many of these ideas. And, you know, I think one important thing that is important to us in terms of invention has been sharing that invention rapidly with communities. So this is literally an outcome of what happened in COVID. With several of the students that are here and many collaborators, we built and designed an ICU grade ventilator, completely open source framework, we partnered with an entity in India, and I was thinking about manufacturing at that time. And this entity had a capacity to make aircraft engines, but it had never made a medical device. And so it's a little bit ironic to think about that sometimes manufacturing capacity and insight are literally embedded in our communities, but not pointing to, I mean, between military engines and life-saving devices, I would have thought that, this is something that an entity like this should choose. And we did this with an entity in Nepal and in Kenya. And now this entity actually has a biomedical division after this intervention. One of the things that I want to mention is let's talk about diagnostics very briefly. Of course, all of you know about COVID and what happened, but you might not actually know that for around 3.2 to 4 billion tests, that this is a year and a half old, less than 0.4% of those tests were actually done in what would be described as low or middle income countries. So massive disparity when you think about diagnostics. And most of the infectious diseases, we actually see them around the world. So even if you threw a dart randomly, we need a much larger capacity to be able to diagnose and detect infectious diseases. This has been something on our mind for the longest time because we work on malaria, TB, schistosomiasis, many of these pathogens where we keep seeing over and over again our diagnostic capacity doesn't exist. So we took that as a challenge. And again, this is just to highlight to you, out there is plotted the probability of where the next big pathogen would come and also plotted the top manufacturers of diagnostic devices. So you can imagine that we just have not been able to build that capacity. So I am looking at the clock and I have this tendency that the talk will essentially exponentially accelerate. So you should just be ready for it. But so we've been thinking about this idea is could you put diagnostic manufacturing capacity like a factory in a box? Could we manufacture every enzyme, every molecular component that you need, the entire gadgetry, all put together? And rather than be thinking about a test being shipped, it's the capacity to manufacture those tests being shipped. And one of the challenges for us was we had learned a lesson from Liberia because when we visited, we realized that the Ebola infrastructure that was put in 7-8 years completely dissolved away because every cartridge was $50 to $60 while you have a daily income of a person that might be less than 50 cents sometimes. And so you realize that it's just, even for diseases where we have a vested interest, because Ebola didn't show up here primarily because it was stopped at the front lines. And, I think this is an obvious thing, hasn't been done even till today. We started thinking about this and we came up with this idea of building and designing a diagnostic test that would be as easy to run as making a cup of tea. Yes, you got yourself a microscope. Go ahead.
Explain a little bit why it's so important to manufacture.
Yeah, I think one of the problems is people's priorities shift. So, vaccines has been another set of an example. Also, there are tens of thousands of diseases, and you can be manufacturing here, but you don't have an incentive to build and design because you don't understand that market. And there is a lot of political reasons to believe that many a times it's, money talks. So when COVID vaccines were put in place, many African governments and places actually said that we are willing to pay the same sets of prices. But there are all kinds of diplomatic reasons why many of these tools were not made available equitably, even when price was not a factor. So I think the challenge that we have to face and think about is eventually we need to be able to build a far more robust infrastructure. And again, we can actually do this from a context of technology because rapidly being able to tailor the sets of solutions to the sets of diseases is very important. So how do you make a molecular test like a cup of tea? That was the device we invented. And the only reason I just want to show you, it actually uses just some really clever tricks around from thermodynamics. It uses differential heating in these sets of chambers and heat capacity of water itself as valves and pumps. It's a single shot device where we actually exploited how ballpoint pen manufacturing works to be able to build this. And the idea is that it uses zero electricity, has Primarily everything, it's a little bit designed like a Russian doll. And we can currently, we did this going from what my kitchen table looked like to actually running a clinical trial for 1,000 people who, without any training, just a video, are actually running this test. And the test works. But one of the big things that we ended up learning and doing is actually building a manufacturing capacity for it in the lab, because we wanted to understand what does it mean to design a manufacturable test. So I'm going to pause here because I like, this is a photograph from Liberia. And now we're running a clinical validation study in this in Liberia. I already talked about the test. Does anybody see another very important medically relevant technology in that photograph? The motorcycle, absolutely. You know about riders in health. That motorcycle is the ambulance. That motorcycle brings a pregnant mother or a very sick child to the hospital. That motorcycle was not designed as a medical technology, but that is a key essential component. And so sometimes when you're thinking about this, when technologies become accessible, people tailor them. And this is another reason. Rather than us choosing what people would use this molecular diagnostic test for, that capacity to be able to use a set of a tool for all kinds of applications, and that started to happen for a while. We built a capacity to manufacture this, and we actually realized that we can completely transform how we do protein purification and manufacturing in situ. All of the factors of everything that's needed in this device made in-house. We picked up a giant truck to test whether we could actually put this factory inside a container. And now we're actually building a small building in Senegal to prove this, that a single shipping container can have the capacity to manufacture diagnostics end to end. Raw materials going in, everything built from scratch. So this is an ambitious project. We're excited about this because then you could actually tailor any sets of local diseases that you would like for these sets of problems. Okay, let me tell you another example of funny physics that comes into play that has to do with sample processing. Now I go back way in Uganda, 2013. I was having a conversation with a friend of mine who was a community health worker, and he had a little centrifuge. I know many of you use centrifuges, used as a door snob. And it was a $3,000 centrifuge, super fancy. I was like, wait a second, you're in a clinic. Why are you doing this? He's like, Manu, we haven't had electricity for the last 6 years. It serves the purpose. The door doesn't bang every time. It helps patients. Let me use it as a doorstop. And on the flight coming back, I was just so disturbed. I started thinking about spinning. And of course, if you think about spinning, you have to think about toys. So I first thought about yo-yos. Do you guys know what the world record for a yo-yo throw is? Any guesses? Just put out a number in RPM. Huh? 1,000? Yeah, so it's roughly around 4,000 RPM. I had a circus artist in my lab, Dino, at that time. He was trying to teach me how to throw a yo-yo. It didn't go so well. I was like, no, this is not going to work. If I can't learn it, it's going to be hard. But then in that process of playing around with what types of spinning toys, we actually stumbled upon something that I used to play as a kid. That's on the right. How many of you have done that before? So that speaks to the age of this group. Because the younger, when I talk to high school kids, they're like, what are you talking about? They have their fidget spinners. But anyway, that toy is actually very important because that happens to be the oldest toy in history of mankind. So 4,000 years ago, all the way, every culture has used, the Greek culture has used this as a musical instrument in funerals. In wet cultures have them, and it's been found in Mohenjo-daro. And the irony is, out of all of this history of being the oldest toy for mankind, nobody asked, how does this damn thing work? So we took a step back, and this is how it works. This is a physics colloquium. You can actually solve this. And one of the key things that we had to use the secondary structures that form in DNA. People had worked on DNA supercoiling at that time, and that is key for amplification. And once we understood it, I'll let you guess, how fast do you think we can make this spin? Any numbers? 10,000 RPM? Yeah? 20,000? So we hold the world record right now for fastest spinning object with human power, and that's 125,000 RPM. That's 30,000 G forces and I can pull out a single malaria parasite because it has a slight density change when it's essentially processed hemoglobin. And with that, we can make tremendous diagnostic tests. So just for 20 cents, this is an anemia test. Essentially, in 90 seconds, you can pull out the packed red blood cell in plasma. We can do this for parasites. And again, just sharing, of course, the physics was fun, but we started sharing these sets of tools. This is one of the clinical validation in Madagascar. This is a chief. He had to approve for us to work in that place. And again, sometimes you make something and you're very scared. Oh, is this equation good enough? Should I show it to somebody? You built something. It's very important to share it because one of the visceral, of course, his smile tells it all, but the idea that a medical device is something that they can see and understand was very important. And the other aspect of this is just for you to understand the social structure and the context you're working in Madagascar. This is a village out. And in that room, this is essentially where big decisions are made. And if you notice in that, there was only one woman in this room. She was sitting right behind the chief. Women are not allowed in that societal framework in these decisions, but she is the community health worker. She's also the teacher. And that's sort of really empowered in the sense of being able to engage. And again, this is something that's come up over and over again in global health. Majority of community health workers are women. They understand the sets of contexts and the sets of challenges. And there are many schemes now to be able to support and being able to build businesses around supporting these women. I'm sidetracked, but it's important to sort of understand sometimes that the structure that you're also dealing with is also challenging, as is equally important as a part of a challenge. So anyway, that was a platform. Lots of people started building these. We shared all kinds of instructions that now led to finally several other tests. This is a bacterial test that's actually out there now. There are PCR tests on this platform. And when COVID hit, we actually also built another simple diagnostic test that operates in a similar but slightly different principle. You just got yourself a microscope. Yes, what's your question? Sorry. I'm just...
Is it like a spit test and then you centrifuge it, or what?
Yeah, so I think centrifugation is this process of pulling out a needle in a haystack, and then you can build anything on top of it. So in this particular system, we are essentially doing a process called RNA extraction, and that requires the centrifugation step. In other sets of tests, for example, the urine test that I talk about, centrifugation is key to be able to separate out the bacteria from the urine to then run the test. And many a times the test has to be run in a fluid that is different from the fluid that the sample was in. So centrifugation is very, very common, and it's just a key ingredient, but you can build the entire test now inside this object. So for example, what we have shown is we can essentially do 5 different steps. We can build these mechanisms to build a lot of complexity in this tiny little disc of plastic. Okay, I'll keep going. I want to talk about this because you mentioned materials. Yes. Yes. Yeah.
So can I put that as a question? What are the areas that are applying research for going from something that's in the lab, like in electricity driven usually something that you would do? Is it just, did you just find that a lot of this is accessible, just it's a lack of thought, or is it some development with respect to like I think in biology and diagnostics?
No, I mean, the most simple thing that I would just answer this way, and then we can talk afterwards as well, is just we have to understand the problem. I think that's what's lacking most of the time. And we're trying to solve these big problems. I don't think you think what the actual problem is, and it might not be where you think the problem is. So, from a perspective of this, for us, we have a very tight bar of like, okay, we have to be able to do this, but not add more than 10 or 20 cents to the overall cost of the test. A lot of ideas fall out. You just have to be able to do that at this price. But at that same time, being able to understand the constraints of the problem, I like calling this thinking inside the box. You should first draw the box, and that box is what will scale, and then fill it with ideas rather than the other way around. We get so attached to our ideas often, and that really is a problem. Okay, I'm going to keep going. I want to mention a few things. Give me like 10-ish minutes, and then I'm going to take a lot more questions because I've just started. Okay, I want to talk about this because you brought up materials. Plastics is something that I told you. I was shocked when I read the statistics, and I grew up in India, and I should have known better. But a couple of years ago, I was reading this article, and every month, 1.8 billion people menstruate. And currently, the statistics is 500 million of them have no access to what you would call any products that are associated with hygiene and menstrual care. And that's a number that's so astronomical. I mean, we're even just talking about from the context of incredible number of health challenges, educational sets of contexts, 100 million girls not being able to go to school because of something as simple as that. And, when you talk about technology, we would say, oh, why haven't we solved that? And ironically, one of the things that happens is all of the sets of things that are even out there are essentially plastic. And lots of cultures that's not accepted. Sometimes it's the cost that's too prohibitive. So we started thinking about this primarily from thinking about local materials. And we realized that we built an economy on cotton. But cotton is actually getting more and more and more expensive. And in the next 15 years, it's going to be very difficult to build a lot of infrastructure on cotton because cotton requires a ton of water. It's from a climate perspective, it's going to be the biggest hit other than the food crops itself. And the question we asked is, and majority of these sets of lacks that we saw them in arid areas around the world. And to be able to build a biodegradable pad, we turned to this object. All of you have had cotton candy. It's kind of magical, like what is actually happening there. There's such cool fluid physics going on. This is called centrifugal spinning. There's a massive disk that's spinning out and generating these sets of fibers. Anyway, so we thought about this because we had built a factory for essentially making N95 mass materials in the past, and we turned that same sort of a capacity to then be thinking about menstrual pads. So again, factory in a box for making the highest grade materials for menstrual pads. We did that, that's now published. One of the discoveries that we made is that you can actually take a plant, this is a cactus called sisal. It grows across Africa, just doesn't need any water, and you can actually convert this into an object that beats cotton at its game. So 1-to-1, it can absorb more water. So that's what sisal is. And I'm very excited because now there's lots of entities and people interested in scaling this up. We're scaling this up in Kenya. This is sort of one of the factories that we're starting to build there to demonstrate that you can do and generate. Again, a plant that has been there right in front of us for generations. I mean, of course, everybody's had tequila here, right? Before. That is an agave. It's the same family of plants. So again, something when you think about materials, you think hard about what is the physics of absorption. We were able to show the reason why this set of a material is actually good enough. Okay, I want to share this because this is a continuing project. We don't know the answer, but actually has sheet mechanics. I know many of you work on flat sheets, so I want to just share this. The next slide that I'll show you will be a little bit gory. So if you want to look away, you can look away. But we started thinking about ostomy bags maybe around a year ago. If you think about this, roughly around 1 million people are walking around with this. When you have many types of cancers, you have a hole literally, and you poop right outside your intestine. You can see the person's intestine into a tiny little bag. Uncomfortable, but it saves the person's life. But when we started looking into this, we actually realized that, around 1 million people are walking with these bags in the United States today, and between 52 to 43% essentially have incredible complications because the pH is very high and it burns and the whole thing leaks. And of course, the cost is a huge issue to a point where people make these bags out of jars, cutting it open. At this moment, you can see this with a belt. That's the reality of our world. And slide, tells you mathematically why this is hard to build, even if you had all the materials, is because of all the curvature which is dynamically changing on a stomach. So how do you actually put something that will stay on for at least even a day or two? And that's what the reality of many of these sets of structures. So because you have to wear it all your life, any sets of incisions that start to happen essentially generate massive infections around. And it's really terrible. We've been thinking about this from, many of you worked on these sets of problems. How do you take a flat sheet, stick it to a curved surface? Now this curved surface, the twist in this is actually dynamic. We just recently built something to be able to emulate this. And I'll just show you why these things fail. There's a couple of ideas we're working, but you'll watch a movie and what's happening is these delamination cones that travel. So this is a stroboscopic movie. I'm not showing you the up and down curvature change, but what you're watching is these sets of delamination cones, and over and over again, we see this. And once we understood this, we were able to redesign the bag to essentially stop this. And right now, some of the students are in India at this very moment, and we're at a hospital trying to test this. Okay, I don't know what's happening with the... Okay, I'll keep going. I can also mute my computer. Now I'm at a junction. Okay, you know what? I'll keep going. And can you still hear me? Yeah, just tell me when to stop. So, yes. Okay, mosquitoes. I brought about mosquitoes. And again, a friend of mine did this calculation, so I don't have to do it. There's a lot of number of zeros there. He was trying to write how many mosquitoes might be there in Alaska. So that's 17, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros after that. It's a lot of mosquitoes. So when you think about the sets of challenges, this is why these diseases have been there forever. We started thinking about this problem and realized this is how we track mosquitoes. This is a postdoc in Australia. I'm glad it's not you. They take a tweezer. We call it the mosquito bucket challenge. There's maybe roughly around 30,000 mosquitoes, and he is putting them one at a time, observing and watching and speciating them. Exactly how 150 years Ronald Ross, when he discovered that mosquitoes transmit malaria. And then again, we all carry, I'll play this ringtone to tell you what has this got to do with mosquitoes. Can somebody tell me, what are you listening to? Do you all find it musical? Or this is the 40 deadliest mosquitoes in the world that we have taken their buzzing frequencies of flight. Mosquitoes are one insect that essentially generates highest wing beat frequencies. There's some idea, but we don't have complete ideas around why would that be. And of course, I've played around with it to make it sound musical. But the thing I wanted to say is mosquitoes mate in flight, so they like to generate different frequencies. And if that's the case, we essentially built a cell phone app that can, a little bit of machine learning. Any of you can now take out your phone, record 30 seconds to 15 seconds of an audio, and we can essentially, from a $5 flip phone, which there are billions of, you can essentially tell what mosquito is flying around. And I think, again, much of this relied on the physics of mosquito flight. Okay, another problem where physics helped us a lot, this is on schistosomiasis, the disease I talked about. Imagine if the only source of water you had was infected by a deadly parasite. And if you ever touched that water, you would be infected for the rest of your life, and around 30 years of age, you would die. Roughly around 700 million people live in the world today with this specific problem. Millions of deaths. After malaria in neglected tropical diseases, this is one of the most important diseases that nobody talks about. We started thinking about this problem from a diagnostics perspective and realized that the kids, so this was a school we were running a study in, 70% of these kids were infected. And then 3 months later, even when they were all treated, they get infected again, because of course it's an environmental disease. If you go touch the water, so if you like swimming, and if you are in many of these regions where schistosomiasis is, you should rethink about swimming. But I think one of the first factors for us was we have to get into the water. We wanted to find the parasites. So these are infected waters in Madagascar and Senegal. We call this technique shovelomics. You take a shovel and you dig for snails in infected waters. We get all the snails, we get them out. We're trying to understand where the parasite, we can't find the damn parasite. And then one day it occurred to us that we should just first understand the parasite. So this is what this parasite looks like. And there came out a really beautiful physics analogy to this, that this parasite, Purcell had said that you need 2 active degrees of freedom at low Reynolds number to swim. This parasite didn't read that book and actually came up with elastohydrodynamic trick to be able to swim using these elastic tails. The physics was really interesting, but I wasn't happy because it hadn't made any dent in the problem that we started thinking about. Very recently, we actually realized another thing for why this is not published, why we couldn't find this parasite. It turns out that the parasite actually latches onto the interface and it swims on the it's like surfing. And this is a completely hydrodynamic interaction with the surface, and that's why we couldn't find it. But why would it do that? For dispersion. So in an entire pond, what this is doing is utilizing the skin effect. Because of the winds, it can't swim that far. It only has around 12 hours to find a human, but it's using these wind velocities. So when it's released anywhere, it completely covers. I mean, the R naught for infection for this parasite is now 100-fold higher because of this trick. And we didn't even know. And, again, going back to the context of physics, now we can think about, could I redesign an entry point that would change the dynamics of where these parasites get trapped? Now, one of the big things that we are thinking about is also, what can we do on the surface to mitigate? And it turned out that we did many tests with surfactants and no effect. And then we went to Senegal and we tested this out in Senegal, the same experiment, and pollutants actually suppressed. And of course, that's not what I'm advocating, but I'm just stating that it's this ironic twist. But if we hadn't understood this interaction, we would not have known. Okay, I see the clock. Maybe we have 2 more minutes. I should tell you about microscopes. I love microscopes. It's one of the most important tools that I think about understanding and building intuition for the small world. And for many years, I've been building and designing and scaling microscopes. This will answer a little bit of that question about scale up. But going back to malaria, one of the first things about malaria is this is what malaria diagnostic looks like in India. That's a paper for Mr. Juan Gimsa, 1904. And currently, this is the WHO gold standard. We're still detecting this disease that 200 million people get infected with. That's Prem and Durga essentially running a malaria. If you ever get tired of doing microscopy and you think you're working very hard, these guys are in there for between 10 to 12 hours every single day doing diagnostics. And one thing we asked ourselves is, now we have self-driving cars on one hand, and then we're still doing this. And we asked ourselves a question, could we really build tools that are completely modular that will do this in an autonomous manner? It took us a long time. We started working on 2014, and now there is a product that we're releasing that, of course, it's all possible because of these NVIDIA chips that are in the cars themselves, where we can do completely autonomous, roughly around in 5 minutes, we can image the order of 20 to 30 million cells. And a human is imaging around 3,000 to 5,000 cells in half an hour. So you can see the kind of sensitivity and specificity you can build. This is what the data and the instrument looks like. And why were we able to do this at this speed? It's not a flow cytometer, but we realize there's a trick people use in astronomy that you actually measure a spectral signal. And so you can actually see here, the parasites are slightly greenish and the platelets are slightly bluish. And that's the trick we're using because we're measuring the DNA to RNA ratio in a cell. And that becomes a signature of the parasite. And just that trick alone, we've been able to now build this instrument, scale this. This is now the first real-time diagnostics for malaria using imaging. It roughly costs around $3,000 to build. And now we have community partners, 25 countries across Africa and India that are testing the tool. I'm very excited about this because now we essentially have the capacity to not only implement an infrastructure, but to also be able to keep a tab on how the disease actually spreads. So real-time diagnostics, which is what's important. Now, a little wrinkle in the problem, again, going back to physics. In India, when we implemented, this is what our smears look like. And I was really upset. We had worked very hard. We had trained these people. This was a really good partner. I knew that they were doing the right thing, but nothing that they would do would change the smear quality. I couldn't do anything with it. I said, could you send me a picture of how you make the smears? And that's the picture my collaborator sent me. They were literally making smears in the house or on the street. And we actually realized that making smears is a non-trivial problem. So I don't know if any of you have thought about this. This is what we've been doing for the last 100 years. You take a drop of blood and you wait and you just slide. And you have to just get it right. You get this beautiful smear. Otherwise, you get gunk because cells start piling on it. You know, people say that physicists like watching paint dry. It's related to that problem. It actually is a thin film Landau. But with colloidal, we solved this problem, and we essentially built a tool now that using a 17-cent syringe, a gasket from a bike, we can essentially make this constant velocity actuator with no electricity. And now this is how Inkwell works. It basically, for the first time now, for maybe a couple of dollars in parts, we can make perfect smears. And this is what's needed if you're going to have, say, 20 million or so cells being imaged on a single glass slide. And, you know, of course, I'm always excited about the microscope, but when I show both the microscope and this, all my collaborators first want their hands on this guy because it's like, you know, it's been such a pain for the longest time. I'm just giving you another example that unless we had understood this problem, there's no way to be able to build and design this. Okay, I am going to tell you something about education and the ocean in the negative time I have. I should tell you something about the ocean. I think it's... Okay, I think I told you the ocean is important. This is what worries me sometimes because what had happened, you know, almost 30, 40 years ago when the first bathysphere was put out is people had made this idea around how carbon sequestration might work, which is called this marine snow. It's this object that falls from the bottom. And if you've ever been to mountains of Dover, this is literally the best carbon sequestration technology that we have. This is literally built of single coccoliths that are 5 micron in size. The entire mountain is made of living material, which has now died, sunk to the bottom, and has sequestered carbon. And one of the big things around this is when you look at what's happening, you know, these are titles of real papers, what the dash is wrong with the current carbon budget. I don't know if many of the editors will allow me to write that title. But one of the things that's important is the biological components are missing. And the key biological component here is how heterogeneous life forms build this beautiful soft matter that I call marine snow, which is an aggregation process that comes together, and its sedimentation dynamics is what determines this. So we built a tool to actually test how this works at sea. And one of the things that becomes important in this framework is the tool allows us to watch a marine snow particle essentially sediment over kilometers. And the idea is fairly simple. It's this giant wheel where you take the two ends, you mix them together, and there are 2 points we can levitate. You can watch living organisms in it. But what's most important for this context is we can actually directly measure carbon sequestration. And the reason I'm spending so much time just talking about this is we've discovered something that's disturbing, which is now this is a marine snow particle. This is the highest resolution imaging that's ever been done on a sedimenting particle. We collected this around 300 meters in depth, brought it back, and now we saw something. I don't know if many of you do fluid mechanics. You should notice something quite bizarre. Do you notice the water behind? It's like as if it's actually traveling with it. It turns out these single cells are secreting a massive amount of mucus parachute. And because of this mucus parachute, the entire structure goes from sinking 200 meters per day, which would give you a massive amount of carbon sequestration, to 0 meters per day. And we say this, like we've been using a Stokes law, size of the circle of the particle, that has no meaning. Stokes law doesn't work here. So we had to come up with a new framework to be able to build a modified Stokes law for this, which we can explain this. But the sad part of this is this measurement told us that we have an error, which is 100% error in our current predictions of how these particles sink. So if you were to think about the total amount of carbon for what we know works, there's a massive error because we didn't account for this simple biological parameter. So again, another example where when you take physics into account, it actually matters. Okay, so while we're at the ocean, I'll say something about plankton. And then Leo, I really mean it. You can stop me anytime. So I think this one is important for slightly different reasons. I told you about citizen science. One thing that makes the ocean work is this incredible soup of life. Of course, it's beautiful. We study this because it's just remarkable life that we can't explain. We all came from there. In your veins you have an ocean in your veins because the composition of many of the ions that are flowing through your body are because all life came from the ocean, and it's the same sets of concentration. So whether you like the ocean or not, you're carrying one with you. One of the challenges that we faced is we have absolutely no idea who's where. The ocean is incredibly dynamic. And we started thinking about this, and I met this sailor. He's a very young person, 25-year-old. He stopped at the lab at Stanford, and he was the youngest person to cross in the winter this Canadian passage. This is his passage. And he goes with the chicken, so Moana. I think it's not just for the eggs, it's also company. He's a solo sailor. But what we learned and thought about is at this very moment, there are 20,000 sailboats at sea right now. Recreational sailors that are passionate. I pay roughly around $60,000 to $70,000 per day to be at sea to do my research. Let me repeat that, $60,000 per day. So no wonder we don't understand anything about the ocean. And we thought, what if we could actually utilize this network to empower them to be collecting scientific data? That led to this program with a partnership with Plankton Planet, where we did sequencing, and we essentially built imaging systems, which you can see one of those now right there. This was the first version we built. When you think about writing a paper, we spent an infinite amount of time teaching people how to build this tool. Any of you is interested, $300, you can put this together. The entire kit is online. And we started sharing them. This is the type of data that comes out of it. This is a bioluminescent bloom being caused. Now you can watch single cells, and all the instructions are online. And this is literally a one-to-one match with an instrument that costs $100,000. Yes. Time. Okay, I will shut down now. And these are people just like you who heard about it and built one and are now contributing to global data sets. Okay, I will stop by this last picture that I want to show you all, which is, how many of you know about Foldscope? Maybe I don't have to say anything. Okay, half of you know about it, so tell your friends about it, and that's all I have to say. I'll end here because I think it's important. Anyway, Foldscope is a microscope that costs $1.75. It's made out of paper. We can do 700 nanometer resolution at this price. At this point, we have, over the last 10 years, we built the first 100,000 in the lab, scaled it up. There are 2.5 million users at this point in 160 countries, 60 distributors, and it's just for curiosity. You go do whatever you want. I've just written one paper describing this. There are 700 papers, people describing new species. And I think I want to end with this I love this photograph whenever I talk about Foldscope. These are their parents are not sharing the microscope with their own kid. And I want you to be that parent for a very simple reason, is that you share science and your passion for science primarily by just embodying what you do. And you share that with people around, and magical things happen. And one magical thing that I want to end on, of course, this is used in many different contexts, from animal, plant health, vector surveillance. These are fishing villages. This is Iraq. We work a lot in conflict zones. We work in prisons, Afghanistan. This is Lebanon. But I want to end with this note of, why I want to emphasize people are still the most important tool, and it's the empowerment of people. When we released this tool, I got this email from a person in Tamil Nadu, a language that I don't understand in Tamil, and he said that I teach this 15 children's school. Will I send some Foldscopes? Because of Google Translate, I don't read my email. Everybody knows that, so it can be on record. But rare occasion, I read it. And I sent him some scopes, and he wrote me back, and I would send him more scopes, and we built a friendship. I went to India, I saw him, I trained him. And then one day he sends me an Excel sheet that had 95,000 entries. and another column with 12,000 entries. And then when I translated, he said, oh, within the last 4 years, that's the number of kids he had trained. And I didn't believe him at first. So I went to Facebook and I became Facebook friends with him. And every single day since I had met him, he was out there running workshops across the country, 30 to 40. If I go on Twitter right now, I can guarantee you Mo is there somewhere teaching someone how to do microscopy. He has no education background. He doesn't have a degree, but he has passion and he cares about people in communities. And I think sometimes when we think about scientific tools and their roles, we forget the superpower that's associated with people. That's the same story that plays on over and over again. So I'm hoping that there is one Mo in this room, and that would change the set of a community that you care about. And that's really what I came here to tell you, is that it's not about the tools, it's about building this sense of community and asking yourself a question, how do I engage? Because all of these problems are astronomical. If none of us engage, they will remain that way. And you will just pass them on to the next generation, and it will be compounded over and over again. So any bit of time that you have, think about these sets of ideas and problems. And I can tell you, it will be an intellectually exciting journey. It's not just a side thing. I mean, I have absolute joy when we solve these problems, just like you would solve any other problem. And I think as a community, we have to embrace the fact that often enough, this torturous path of solving these sets of problems is important. So take that as a challenge. I'll close here, and I'm around. We can talk. I'll end with this photograph. This is some friends from Liberia going to school. And you can think about, why are these somewhat older kids going? They're actually going to middle school, like maybe 8th grade or 5th grade. But okay, I'll end here. I think otherwise I'll miss my flight too.
We'll take some questions from the audience.
Yeah. And then, by the way, Planktoscope is running live here. So if anybody wants to then come and see it, we can pour the water from your pond or your dorm. If you're curious what is in your water from your dorm, we have the tool to test it. Okay, questions?
Questions? Yeah, please.
Diagnostic testing, how are you protecting this data that is like, I would imagine maybe, someone was in it could be like some good company, would find this data useful, using it, using it appropriately.
So I didn't get the question, but maybe if you meant how do we validate it, we basically run clinical trials across the world in many places. We then run usability trials, which are different from validation trials. Is can somebody actually do the test or run them themselves? And then much of the rest of the scale is driven by partnerships. So for example, with SnapDX, we are building a partnership with Institut Pasteur. But the idea is once we can demonstrate it, that we can manufacture it there, the idea is that we could manufacture it anywhere. And much of this work can't happen without engaging with other entities as well, because as a small lab, it's quite challenges to make. We made 10,000 of these tests in the lab. We made around 100,000 microscopes in the lab. And a lot of my neighbors don't find that fun, but that's what we do.
Marcus?
Yeah, it's fascinating. Absolutely. But there's one thing I'm an ignorant business to what people at the medical is telling that you can diagnose these approaches to get all the information about the potential patient. The problem with that main challenge is really how do you administer treatment and how to monitor. And even if you look at what they call a affluent privileged society, like subsidized countries, you look at in hospitals, people get their medical prescriptions, and a shockingly small number of actually, whatever, 20% are actually doing what the doctor told them.
Yeah.
Follow.
Yeah.
Is it actually sad as it is, knowing what the knowing what treatment that works
Yeah, I think there's a very simple answer to this. Yeah, there's a very simple answer. You know, healthcare is delivered, there is a local context to it. So every local place has subtle sets of problems. If your hospital right here didn't have any diagnostics, I think you wouldn't be able to do anything to begin with. It is the frontline mechanism. Now we happen to be fortunate that we can do that. Then we have to tackle the next set of a problem. For most of these infectious diseases, it's 1 or 2 pills and you're cured. That's it. We've had those pills for the longest amount of time, but we've been just randomly giving them to people. That has now led to antibiotic resistance. So for malaria, we have anti-malarial resistance because people just go to the store. You have a fever, and you go buy it. And at this point, the frontline drug, artemisinin, is actually out of commission. We're starting to worry significantly about what is going to come next because we don't have a candidate. So you should think of this as layer-wise problem. Just because there are problems further ahead doesn't mean you solve these sets of central problems. And even from a diagnostics perspective here, I wish we had better diagnostics here. I mean, much of the whole point of building these, we talked to the FDA, we're engaged in that conversation. We need molecular diagnostics to work in people's hands. It's as simple as that because you would know what you have. Currently, the amount of delay that it causes is a huge set of a problem. You know, so how you implement services and build infrastructure around this is a very local problem. Lots of people get involved, they find their ways. Lots of very thoughtful people are engaged in building a better structure for health. But most of the time, the tools that they have are absolutely terrible. So they do what they can. I mean, just look at the doc. How overworked are they? Just if you go to a talk, I mean, the amount of time they spend there is just, you know, often enough, these sets of decisions are much more driven by, this is a complex set of an issue, all the health insurance and other sets of things. But I mean, I chose to work on diagnostics because I feel very strongly about the fact that we are treating people when we're blind. I wouldn't want to be treated that way. I wouldn't want my kids to be treated that way, that you have absolutely no idea. And I mean, it is actually fascinating that many of these healthcare systems that are globally implemented, including the United States, primary healthcare is exactly where we should be investing the money. When it comes to the hospital, it's already too late. And I think that's the attitude because you don't make the big bucks at the big hospital. So there is a little bit of a problem of how we have commoditized healthcare to begin with. And again, these are bigger issues than I could tackle. I just sort of focus on where I feel the big gap is.
Good question.
I question whether you thought about trying to collect all this data, because with climate change happening, I'm sure stuff's going to start migrating.
Yes.
And if doing it cheaply is tricky as well.
So here is directly I showed you this picture, which is a consequence of this map. These are the people that saw the paper, went to the website, built the instrument. And I love that. There's a little dad right there. He's with because the dad probably can't sleep with his baby in his arms. But that's what's been happening. So over the last, since 2021, when we released the first version of the tool, that's now number 3, these are literally entries from around the world that have been pouring into this central database that we created, completely autonomously. And kind of this is one of the aspects of this. For Foldscope, it's the same. There is a community website right there, terabytes of data sets. That's the link to the website if anybody's interested. While I talked to you for the last hour, there must have been posts that have come literally at this very moment, somebody describing the microbial world that they saw. And so I think data is an incredibly important part of it, but I think it's a step further. These are little stories that people tell. So we try to let people have a voice. So this is not Wikipedia. It's not about being right. It's about sharing what you're thinking. And so all kinds of goofy articles will come in on it. And people are learning how to be a scientist as well. So there is this sense of a scenario of sometimes some scientists, without naming names, we've been too snobbish to say, oh, this is the type of data you should collect. Why should anybody do anything that you want to tell them? So building that flexibility that here is something that's necessary, having them understand that, but also letting people play with these tools. That's really the balance. I see a question right there. Yes. Are there a lot more creatures found? Yes. Should I open a new slide deck? These guys are laughing, but
We have 500 to go.
are there other creatures? I'm about to open a new slide deck, yes. No, I have to answer him. I'm sorry. The answer is yes. There are a lot of creatures out there when you look for them. They are all the way from the surface of the ocean to the bottom of the ocean. And they are wonderful and beautiful in ways that you can't even imagine. It's like if you wanted to search for alien life, you should go to the ocean, quite literally. And what is so amazing is we don't understand how any of them work because we don't have that kind of a framework. And one thing that I have to say is if some of you have not appreciated or thought about the density of life, I mean, this is kind of one big challenge that we face is the ecosystem that I was on this dive at night and it occurred to me at that time, and then I went back and pulled this is a night dive and we just have a camera running. And this is the density of stuff in sea in this dial migration. So, I mean, how do you understand a soup of life? We're still struggling understanding one. I know, like when people say ecosystems, they're like 2 species, 3. This is what's going on. And every one of them has this unique, wonderful mystery that you can think about. So you have a future, like all these people, even if they work very hard, are not going to be able to discover. There's so much more. Maybe around 99% of life on Earth might still actually be undescribed.
How deep is it?
This is surface. So this is literally on the surface because, this is kind of what's mind-boggling is, I mean, it's the largest biosphere on this planet by far than anything else. Yes. Yeah. And I think that's an excellent idea. And just like you, I did that today. And this is the Kittredge Pond. And if you come down here, we can look at what's in here. And, the irony is every time I'm looking, it's the most fun moment is you just say, what the hell is that? And we had that last night with some of the students where we were just all flabbergasted what we were looking at. It's the best way to learn science is to just dive in. Okay. I don't know what I'm doing. You think I'm doing global health? That's very kind of you. Yes. There's some questions I'm not allowed to take. So, yeah. No, I mean, I think I'm excited about certain sets of things and ideas. And of course, it's really the passion of people that we build a massive group of teams. Often enough, it's not, we try to figure out where would a piece of work fit. So when you kind of strip that all away and you just say, I'm passionate about this idea or this, then it happens on its own. It's, often enough, and it takes time. I mean, we've been at it for the last 15 years. So it's not instantaneous. We sometimes zoom in and zoom out and have the capacity to zoom out. I think we train lots of our students to be able to zoom in, where you're really focused on this one thing, but everything that you've learned, if you zoom out, applies somewhere else. Many of these ideas in my head of everything that I talked about yesterday and today are all connected. I don't think of them being applied or basic. I think none of that makes any sense. We should not have split the physics departments into applied and basic. It just does not make sense to me. So it's, you have a career ahead of you, and it just, the most precious thing you have is your time. That's really the most important. And overall, there are some problems that you hear about and you cannot stop thinking about. And then we will muddle over it for 10 years sometimes before we have an interesting idea. So, you should also be collectors of problems, just like you're collectors of ideas. Even if you don't know how to contribute, because one day you'll be waking up, doing something that you're supposed to be doing, but you will actually crack a problem that's far away and far removed. I think this is also why embedding yourself in the problems that you work on is important.
Other questions?
Yes.
Thank you. I have a question.
Yeah, I mean, I think this is a principle like this you could apply to literally everything that you do. And I would argue all the science we used to do was with this. Every scientist was trained to build their own tools. And that is still actually in several disciplines, it really is part and parcel of how you operate. So in some sense, being resourceful and thoughtful about the sets of tools that you need is very important, and it'll be valuable. It's just this match between the things that you're excited about building and the sets of problems, and that takes time. It's perfectly okay to expose yourself to a lot of problems and simultaneously build a lot of different skills. And then suddenly that aha moment happens. I think I try to teach this in the Frugal Science class, by the way, is open to anybody. Any of you can join. We do between 15 to 30 projects in 3 months' time from people around the world. All countries can participate. And this is what we try to do, is I will list all kinds of problems, people who have lived experiences and they are challenged, they think about that problem, will bring that problem to the table, and somebody else from another field will say, oh, maybe we should try that. So I think more of that conversation, find a friend who has complementary sets of skills. And it's much more fun to also tackle these problems as a group. It's not an individual process in some sense, because you might get attached to a solution while you don't truly understand the problem. And this happens very often. And then we just, whatever price point that solution turns out to be, is we think of that because, the first idea you have is just feels so good. It's like, of course, this is what I'm going to do. But the art of this is to have so many ideas that you're willing to strip away all of them until they fit this criteria. So that takes a little time. Yeah.
Okay, maybe with this, we'll thank one again and for a wonderful lecture. If you have questions, come down. You can...
Yeah, and I also have some fold scopes here. So for the folks who ask questions, or anybody, you can play with them, but they're also, you can get them anywhere online.
We'll take a.
Yes, you have to take.
Yeah, no, it's all good. It's
Yeah,
all good. This is
yeah.
so
No,
much
no, no,
more, this is so much more important,
Yeah,
No,
I
this
just
is
thought
the
that
most
it's really
no,
fun to actually talk to
No,
people.
exactly.
Yeah.
Exactly. This is what it's for, right?
Yes.
This is exactly, we can't lose sight of what it's actually for.
That's true. Yeah.
It's when there's no difference, then it's.
Oh, you guys are very kind. Yeah, and again, I'm super sorry. I
hope you recover.
Yeah. I have one more week, but then after that, I'm gonna take off after this. For the questions you asked, here's your little microscope. And then you can put some pond water right in here. There's a little card. I don't know if you like Pokemon.
Yeah.
This is like real world Pokemon.
Yeah.
So you put that in, and then we'll do a quick demo of Foldscope if you guys haven't used it. I took a piece of tape, and Leo helped me catch a grasshopper yesterday. And I bet it's still, is it there? You see a grasshopper in any of those tubes? No, I taken it out. Oh, right here it is. Okay.
That's a whopper.
And it might be dead. Or is it? It is dead. Okay. Do you guys know how they can hear? They make all these sounds, but where is it that this would hear from? On the knees? Yeah, they hear from their legs, and just like your eardrum, they have an eardrum. I've actually wanted to, but I've never seen the eardrum. It's called the tympanic membrane, and it's somewhere on the structure of the leg. So if any of you want to sit down, you can dissect the leg, put this in. I'll just do a quick. Oh, that's gorgeous. I don't want to, it's dead. So I was about to say I don't want to kill it, but let's just take a little piece of this and just think about how remarkable that technology is. I mounted it right here. We take a foldscope, you take that in, you put that out. This slots in right here. And then again, you can mount slides, whatever you want to do. And then there is some amount of ambient light here. So I'm just going to use that. You always use two hands. This is focus. I'm pointing it there, and I'll let you see, and you can describe to people what you see. And I'll just mount a little bit of there's also a little light that I have here. So I'll mount that. So you don't need this if we are outside, but right now, because it's a little bit dark, I'll just mount this light itself too. And then suddenly, then it also has the illumination coming from here. And I am looking. And then the last thing that I can also just show you here is in terms of, I'll add a little diffuser here. This is just a piece of paper. And now, of course, because we're so many of us, we also want to share that. So first of all, take a look now.
It's like a bunch of gray like squares
Uh-huh.
that
yeah.
have like lines in them.
Yeah,
and
yeah. Now
some of
take a
them
look. And
have little divots, like someone poked a pen in each of them.
And so now that's one person that doesn't need this phone or anything. But if you happen to have a phone, then what we will do is we will just record this. So here I'm recording. Here's the poor hopper because I want to know what species it was. And then now, once I have this here, for example, exactly, then we get essentially all of us can see it. So we're going to go up down here. And if I mount it there, so now you can see the veins that he was talking about. Now you can ask all kinds of questions. So first of all, why do insects have veins in their wings? So you can think about structural rigidity, but you also have to realize this is not dead. So they need, each one of these cells actually need nutrients. And so there are these remarkable flow topologies that go through this. And it's a connected network. And then you can ask all kinds of questions about this network. What would be the evolution of an object? And then suddenly I'm seeing patterning. You see, it's digital painting. One of that voxel is totally transparent. And then suddenly this has pigments. And now these are epithelium. I can even go further to see.
What part of it is it?
I just pulled out the wing right there.
The wing. Okay.
So this is that, you see patterning right there?
Yeah.
It's probably one of those sets of patterning. And the field of view here is maybe around, this is around 100 micron when I was completely zoomed in. These veins might be around 20 micron. And I know it's dead because if it was alive, you could actually see fluid flow through these veins. No. The cells are right here. So every one of those dots that you see is a hair cell. This is the wing venation pattern.
The wing structure.
Yeah. But then, I think one of the things about observation is that then you notice, wait a second, in some sides, I see this perfectly discrete structure, but here the coloration is starting to change. And with these hoppers, it's a very important thing that when they change, they transform, they change color. And so that implies they also have the capacity, they have plumage, just like birds have plumage, but they become very different as seasons change. And at some point of time, they also become cannibalistic. And then they eat each other and all kinds of fun things happen.
They last a long time.
Yes. And so, you can start by just poking around and then suddenly ask questions. And that sets of questions, maybe somebody's asked, but it doesn't even matter. It's your own discovery that you're walking through. And then now I can go on the community website and just upload this. And then suddenly that data set and that idea that I just said is shared with everybody. Anybody can work on that problem. It doesn't matter. So I think in science, when you share observations and you anchor that, you're also teaching people how to share and think. And what you would think would be very different from how anybody else would think. And that part is important. So any of you can build it. I'm hoping almost all of you can have it, but this is like literally like buying a pencil. So you can just go online and get them. And actually, maybe I should start with the youngest people first. So who do you think the next younger person? Okay, you are. No, I think I have plenty that there you adamant. It, you go to full, you distribute them. So just pass around. Yeah, this is so you can just pass them around.
Because each of these kids.
It's literally $1.75 gave you. So I mean, that's your. Oh, there is a little coupler that